All right, this is it, the last topic of the term. You made it. So the last thing we're going to talk about in this chapter and in this term is synthesis of epoxides and reactions of epoxides. And so an epoxide is a special kind of ether. It's a cyclic ether that makes a three-membered ring with oxygen as one of those members. So you can see here in this slide that second structure is an epoxide. You can see the triangle. It's a three-membered ring, and oxygen is one of the atoms in that three-membered ring, and the other two atoms are carbons. So we're going to look at a couple of different ways to synthesize epoxides. We can synthesize an epoxide starting from an alkene using a reagent called MCPBA, which is metachloroperoxybenzoic acid. So we can see the structure of MCPBA over there on the right. It has a benzene ring and a chlorine atom on the benzene ring, and two positions over is a peroxybenzoic acid. So notice how that group looks like a carboxylic acid, right? It's got a carbonyl, it has a hydroxyl group, but it also has an extra O. So it kind of looks like a mix between a peroxide, where we have two oxygens bonded to each other, and a carboxylic acid. So it's called a peroxycarboxylic acid, or in this case, since it's on benzene, a peroxybenzoic acid. So it's easier to just remember the abbreviation MCPBA, all right? And that's the reagent that we're going to use to synthesize an epoxide starting from an alkene. The CH2Cl2, that dichloromethane that's underneath the arrow, that's the solvent in this reaction. And so we use MCPBA. So we need an alkene, MCPBA, and some solvent, in this case dichloromethane, to synthesize an epoxide. Here is the mechanism for this. The R in the peroxy acid, it could be a different peroxy acid, but in the case that we already talked about, that peroxy acid is MCPBA, so that R group is the benzene ring with the chlorine attached, metachloroperoxybenzoic acid. So this is a fairly complex mechanism. All of these arrows are in one step. So this is a concerted reaction where all of the arrows take place in one step. This is similar to hydrogenation of an alkene, right? Or when we do hydroboration. Those are both concerted mechanisms where all of the steps take place at once in only one step. We draw all the arrows in the same time. So remember, in general, when we're looking at mechanisms, it's important to separate steps that occur separately. So in SN1, the first step is the leaving group leaves, and the second step is the nucleophile attacks. In SN2, both of those things happen at the same time. So it's important for us to separate steps that occur at different times. But in this case, all of these bonds are made and broken all at the same time. So we draw all of the arrows in the same step. Notice that we deliver, overall what's happening is we're delivering an oxygen atom across that alkene. And so we start with that double bond, carbon-carbon double bond, and then we deliver one of those oxygen atoms across the double bond to make the epoxide, to make that three-membered ring with oxygen. The specific oxygen atom that gets utilized for this is the oxygen atom that's next to the H in the peroxy acid. So notice there's 3 oxygen atoms altogether in this functional group. In every peroxy acid, we have 3 oxygen atoms. It's always the oxygen atom that's next to the hydrogen that's going to be delivered to the alkene to form that epoxide. And so if we follow those first 2 arrows from the alkene, the oxygen atom attacks one side of the alkene, and the double bond attacks the other side of the oxygen. So those first 2 arrows on the left there, that's how we form the epoxide. We're going to make 2 bonds to oxygen, to that one oxygen atom from the alkene. And then that oxygen atom becomes detached from the peroxy acid. So we have to also break both of those bonds that are holding the oxygen atom to the peroxy acid. So there's 2 arrows. The first 2 arrows on the left are the ones that form the new bonds in the epoxide. The next two arrows in the sequence are those that break the bonds that are holding that oxygen to the peroxy acid. So we see that we've got an arrow that goes from the bond between O and H that's going to become a lone pair on the oxygen atom. Because overall the oxygen atom is going to have two lone pairs left over when this reaction is finished. It uses one of the lone pairs to attack the alkene, so it gets a lone pair back when that bond between oxygen and hydrogen breaks. And then there's also a bond that's holding that oxygen atom to the peroxy acid that's between the two oxygen atoms. That bond is also going to break, so that's the arrow on above, that top arrow there. That shows that the bond between those two oxygen atoms is breaking, and those electrons are being delivered between the carbon and the oxygen, so that single bond is going to become a double bond. So try to trace the arrows on the left side and see what the consequence of those arrows is on the right side. So on the left side, we formed those two bonds to oxygen. We've also broken the two bonds that were holding that oxygen atom to the peroxy acid. So one of those bonds broke to become a lone pair on the oxygen. The other bond broke to become a double bond between C and O. Finally, we have two more arrows, so there's 6 altogether. So notice that what was the carbonyl, the C double bond O, that double bond is breaking to become a new lone pair on oxygen, and one of the lone pairs on that carbonyl oxygen is attacking the hydrogen atom. So in the end, what we're left with is just a regular carboxylic acid. It's very counterintuitive how this mechanism works, but we start with a peroxy acid, and a peroxy acid has one extra oxygen atom in it, the difference between that and a carboxylic acid. And after the mechanism is finished, we have a regular carboxylic acid. To me, what's counterintuitive about this mechanism is that the carbonyl, the C double bond O, changes. What was the C double bond O, what was the carbonyl on the left side, is now a single bond between carbon and oxygen. And what was a single bond between carbon and oxygen on the left side is now a double bond between carbon and oxygen on the right side. So the carbonyl changes positions. Which oxygen is part of that carbonyl group changes over the course of the mechanism. And finally, that hydrogen atom was bonded to an oxygen in the peroxy acid, but that oxygen is now gone. It was delivered to the epoxide. So that hydrogen atom is grabbed by the carbonyl oxygen on the left side, and so that becomes the new hydroxyl group for our carboxylic acid on the right side. So stare at this mechanism for a while and try to understand how all of these arrows work together to get us from the left side of the reaction to the right side of the reaction. So another way that we can form an epoxide starting from an alkene is to first make a halohydrin. In this case, we're making a chlorohydrin. So remember, we went over this mechanism when we were talking about the reactions of alkenes. If we just use a halogen like Cl2 or Br2 or I2, then we deliver 2 halogen atoms across the double bond in an anti configuration. So we'd have 1 chlorine on the bottom and 1 chlorine on the top. But remember, if we have water in that reaction, the first step is to make that chloronium ion, right? And then in the second step, water is going to attack the one side of the chloronium ion, and that is eventually going to become the OH group on our chlorohydrin. And so remember, the side of the chloronium ion that gets attacked by water is the more substituted side. So when I have that chloronium ion, it's the more substituted side that's going to get attacked by the water. In the case that we're looking at here, the specific example, both sides have equal substitution, and so water can attack either side. So we're just showing the water attacking the left side, but since the right side has the same degree of substitution, it could also attack the right side. And so that's going to break the bond on that chloronium ion, open up that 3-membered ring, and put an OH group across our cyclic compound there. So then when we see the series of reactions on the top, we start with an alkene, we use water and Cl2, and at the end of the reaction, after all the steps in that mechanism, we had a Cl on one atom from the double bond, and we get an OH on the other atom from the double bond. This is not the complete mechanism that's shown here. If you want to review that mechanism, go back to the chapter on alkenes and see how this halohydrin formation works to trace the entire mechanism. So once we have this chlorohydrin, we can use that to synthesize an epoxide. So the second series of reactions on the bottom there, displacement of the chlorohydrin, that's going to show how we can use this chlorohydrin to synthesize an epoxide. So we've already seen that if we deprotonate an alcohol, the oxygen atom becomes nucleophilic. So that's what's happening in that first step. We use a base like OH-. That hydroxide ion is going to deprotonate the alcohol and leave, take the H and leave a lone pair on oxygen to make an alkoxide. Now that O- that we're left with is a strong nucleophile. And the atom right next door to that strong nucleophile has a good leaving group, a chlorine atom in this case. So that first step is just a deprotonation. We deprotonate the alcohol to turn it into a strong nucleophile. And the second step of this mechanism is just an SN2 reaction. That strong nucleophile is going to attack the secondary carbon with a good leaving group. The chlorine is going to leave, and we're going to form an epoxide. So there are two ways that we can synthesize epoxides. We can use an alkene and MCPBA. That just takes one step. We just use MCPBA, and the whole mechanism happens all at once in that one step. Or we can use a two-step mechanism to form an epoxide. The first step uses Cl2 and water, and then in a second step, a separate step, we have to add a base. So we would add hydroxide, and that would deprotonate the alcohol, make a strong nucleophile, and eventually make our epoxide. So two different methods to synthesize epoxides. We can use this same strategy to synthesize other cyclic ethers. An epoxide is just a cyclic ether, right? An ether has an oxygen and carbon atoms on both sides. An epoxide is specifically a three-membered ring that has an oxygen atom in it. We can also make a five-membered ring that has an oxygen atom in it. In fact, we've seen this reaction, this specific reaction, a couple of times in this class already, where we start with a molecule that's not cyclic, but it has an alcohol on one side and a good leaving group on the other side, chlorine in this case. We can use a base to deprotonate the alcohol, which turns it into an alkoxide, which makes it a strong nucleophile. And that strong nucleophile can attack the other side of that molecule that has a good leaving group to form our cyclic ether. So we don't have to form just three-membered rings. We can form five-membered rings with an oxygen, four-membered rings with an oxygen, six-membered rings with an oxygen. So this is a general strategy to form cyclic ethers. An epoxide is just one type of a cyclic ether. Okay, so those are the only, we're just going to talk about those two methods to form epoxides. And now that we've formed the epoxides, we're going to see what we can do with them. So epoxides are, in general, unstable because they have a lot of ring strain. Remember, anytime we see a three-membered ring, that molecule has a lot of ring strain. And so often the way that cyclic molecules react that contain a lot of ring strain is to open the ring, to make it a bigger ring, or to break the ring open altogether. So in this case, we start with a three-membered ring, a three-membered ether, which is an epoxide, and we can treat it just with H3O+, in this case, water and sulfuric acid. And the first step in the mechanism is protonating that ether, right? The ether is a weak base. There's lone pairs on that oxygen. We're going to protonate the ether, which is going to make it a strong electrophile. The carbons on either side are strong electrophiles because now we have a good leaving group. This is the same strategy that we use with an alcohol. We protonate the alcohol to turn it into a good leaving group, and then we can perform a substitution. So if we protonate this epoxide, we make a good leaving group, and then that epoxide can be attacked in a substitution reaction. So notice that in that second step, we have this protonated epoxide. There's a positive charge on oxygen, and what happens is water attacks one side of that epoxide. This is exactly the same as what happened in the previous slide, where we had a chloronium ion, and water attacked one side of the chloronium ion. The chloronium ion was a 3-membered ring with a positive charge on carbon. This is a 3-membered ring with a positive charge on oxygen. And so water is going to attack one side of this protonated epoxide, and that's going to break open the 3-membered ring. And then if water is our reagent, then the last step is deprotonating that molecule of water that just attacked. And what we're left with in that case is a trans diol. It has to be trans because that second step of the mechanism involves our nucleophile attacking from the opposite side of the ring. So, for example, the OH group is on top, and the nucleophile has to attack from the bottom, which is going to put those two OHs that we end up with on opposite sides of the ring. So we're always going to get a trans diol in this case. However, notice that in this particular instance, both sides of that epoxide have equal substitution. And so we showed the water atom attacking the right carbon atom, but the left carbon atom is equivalent, and so water could have attacked the left carbon atom as well. In that case, we would have the OH on the bottom would be on the left, and the OH on the top would be on the right. So that's why it says that in parentheses, at the end of this reaction, we get a mixture of enantiomers. They're always going to be trans, but the OH on top might be on the left side or it might be on the right side, depending on which side of our epoxide was attacked by water in that second step. We can also form not just a diol with two alcohol groups if we use water, but if we use an alcohol like methanol, then methanol can be our nucleophile in that second step. Methanol can attack our protonated epoxide, and once we deprotonate that methanol, we're going to be left with an ether. So in which case we'd have an OH on one of those carbons and an OR on the other carbon, depending on what our alcohol was. In this case, methanol, so we would have a methoxy group that we added to our epoxide. So we could use water as a nucleophile, and we'd get two OHs, or we could use an alcohol as our nucleophile, and we'd get one OH and one OR. Again, a mixture of enantiomers in this case, because since both sides of that epoxide are equivalent, they could both be attacked with equal probability. We have seen that we can react ethers with a halogen acid, so HCl, HBr, HI. And so this mechanism really works the same way. The first step is protonating the ether, protonating the oxygen in the epoxide, breaking the bond between H and X. That's going to release X-, which is a strong nucleophile, and that strong nucleophile can attack one side of the epoxide to open it up. If our epoxide is symmetric, then X- will attack both sides. Or one side or the other, I should say, with equal probability. So again, we'd get a mixture of enantiomers depending on whether X- attacked the left carbon of the epoxide or the right carbon of the epoxide. And once we're finished with that second step, we have an OH group on one atom, and we have an X group on the other atom, the halogen that we delivered. And remember that when we use HX to react an ether, we generally end up with two alkyl halides. And so that's what would occur here as well. Now that we have an OH, the same mechanism would occur. That OH would be protonated by another molecule of HX, which would turn the OH into water, which is a good leaving group, and then X- would attack that carbon and water would leave. So I'd end up with two X's on those two halogen atoms on those carbons where we had originally had the epoxide. Okay, so all of those reactions that we just showed were reacting acid, right? We start with an epoxide, we put an acid in, maybe sulfuric acid, that's going to protonate the epoxide, and then our nucleophile is going to attack the protonated epoxide. So those were mechanisms that were in acid. We can do the same mechanism in base. Notice here that instead of using H3O+, we can just use OH-. We can use a basic mechanism, use a hydroxide ion. Hydroxide is already a strong nucleophile, so hydroxide can attack either the left side or the right side of this symmetric epoxide to open the epoxide, and we would end up with a trans diol. So we get the same product whether we use H3O plus or OH minus. It's going to react the same way if I'm starting from this symmetric ether, symmetric epoxide that can be attacked equally on the left side or the right side. Okay, so here's the difference. If we start with acid, if we do this reaction in acid and we're opening the epoxide in acid, the nucleophile is going to attack the more substituted side of the epoxide. Notice that now we're starting with an epoxide that is not symmetric. One side of the epoxide, one of the carbon atoms has 2 methyl groups on it, and the other carbon in the epoxide has 2 hydrogen atoms on it. That means that the carbon on the left side of our starting material is a tertiary carbon, and the carbon on the right side of our starting material is a primary carbon. We have a tertiary and a primary carbon. And so once we protonate, there is now a difference between those carbons. It's no longer symmetric. So if we do this reaction in acid, the carbon that's going to get attacked is the more substituted. Notice that the left side, that tertiary carbon, is more substituted. And so if my nucleophile is ethanol, in this case in green on top, the ethanol, that ethoxy group, is going to end up on the more substituted carbon. The ethoxy group ends up on the tertiary, and once I open that epoxide, it will leave an OH on the other side. So I'll get my ethoxy group on the more substituted carbon. If I use the exact same starting material, but instead of doing the mechanism in acid, we do the mechanism in basic conditions. So I don't have ethanol and an acid. I have sodium ethoxide, which is already a deprotonated version of ethanol, which is a strong nucleophile. In that case, in basic conditions down in blue, that nucleophile is going to attack the less substituted side of the epoxide. And so my ethoxy group is going to end up on the primary carbon. So in acid, in green, the ethoxy ends up on the more substituted carbon. And in base, in blue, the ethoxy group ends up on the less substituted carbon of the epoxide. Now, why does this happen? Let's take a look at the mechanism. So when we're in base, we have a strong nucleophile. And so these are just our typical SN2 conditions. So when we have a strong nucleophile, we look for the substrate that has the lowest degree of substitution. Because remember, in SN2, methyl is the fastest substrate, and then primary, and then secondary, and then tertiary. That's the order of reaction when I'm looking at an SN2. So I have 2 different substrates here. I have a tertiary carbon, and I have a primary carbon. Since these are SN2 conditions, the primary carbon is a better substrate for that nucleophile because it's less hindered. There's less steric hindrance. So my strong nucleophile, the ethoxide ion, is going to attack the primary carbon, which is going to open the epoxide and leave a minus on that oxygen, make an alkoxide, and then the alkoxide is going to get protonated by a molecule of methanol. So overall in this reaction, we end up with an ethoxy group on the less substituted carbon because it was SN2, and we end up with an OH on the more substituted carbon, which is the remnants of the epoxide after it gets opened up and protonated. If we're in acid, it's a little bit different. If we're in acid, the first step in the mechanism is protonating our epoxide. Once we protonate that epoxide, we create a series of resonance structures that we can see here. The most stable resonance structure is the one in the middle, which with the epoxide. And that's because in that structure, every atom has an octet. But we can imagine that that structure in the middle is in resonance with the 2 structures on either side, those 2 carbocations. And so those 2 carbocations are not symmetric. One is a primary carbocation, and one is a tertiary carbocation. This is exactly the same as what we saw when we did oxymercuration. Remember, in oxymercuration, we make a 3-membered ring with mercury, and the 3-membered ring with mercury is in resonance with 2 carbocations, and the carbocation that is most stable is the one that gets attacked. So this mechanism is analogous to the mechanism of oxymercuration. It's the same steps. So that oxygen, the what we can see is that the tertiary carbocation is more stable than the primary carbocation. And so once we protonate that epoxide, it's the tertiary carbocation that's going to be attacked in the next step. This is the opposite of what we just said in base. In base, the primary gets attacked. When we're in acid, the tertiary gets attacked because the tertiary is more substituted, analogous to the oxymercuration mechanism. So here's that mechanism. The first step, we protonate the epoxide, and in the second step, it's the more substituted side of the protonated epoxide that gets attacked. So my ethanol molecule is going to attack that tertiary carbon and open the epoxide, which is going to leave us with a protonated ethoxy group on the more substituted carbon. And in the next step, we deprotonate that ethoxy group. And so overall, we end up with an ethoxy group on the more substituted carbon. So just to reiterate, when we're in acid, the nucleophile attacks the more substituted side of the epoxide. And when we're in base, the nucleophile attacks the less substituted side of the epoxide. So what happens if we use organometallics to open an epoxide? Well, remember, organometallic reagents are very strong bases. So these are basic conditions. If we use a Grignard reagent with magnesium, or if we use an alkyl lithium reagent with lithium, they're both strong bases. So we're going to attack the less substituted side of the epoxide in this case. The epoxide is going to open. That's the overall reaction that takes place here. And our strong base, our organometallic, is also a strong nucleophile. And so it's going to attack the less substituted side. So in step one, we have an ether, which is just the solvent, and we use our organometallic reagent. It's going to attack the less substituted side of our epoxide. And in the second step, we use H3O plus to protonate the resulting alkoxide after we open that epoxide. And so notice when we look at our starting material, the epoxide here, the left side has two hydrogens, and it's bonded to one carbon. So that carbon on the left side of the epoxide is primary. The carbon on the right side of the epoxide is bonded to two carbons. There's the carbon on the left and the R group on the right, which we assume is some kind of carbon. So the carbon on the left, excuse me, the carbon on the left is less substituted, and the carbon on the right is more substituted. Since we're in base, the less substituted carbon is going to get attacked. So my organometallic reagent is going to be delivered to the left side of this epoxide, the less substituted side of this epoxide. That's why we can see that R group in blue is now bonded to the less substituted side of the epoxide, and the resulting alkoxide from opening that ring was protonated in the second step, and so the OH group is on the more substituted side. So here's a specific example where we start with an epoxide that's asymmetric. It has two hydrogen atoms on the left carbon and only one hydrogen atom and one carbon on the right side of that epoxide. So the left side of our propylene oxide starting material is less hindered, and the right side of our propylene oxide is more hindered, is more substituted. Cyclohexyl lithium, our reagent in this case, is a strong base and a strong nucleophile. So that means we're in basic conditions. So that strong base is going to attack the less substituted side, the left side of our epoxide in this case. And then in that second step, we use H3O plus to protonate the resulting alkoxide. And so that gives us our product on the right side, where that cyclohexyl ring has been delivered to the less substituted side, and my OH ended up on the more substituted side of the epoxide. If we use a Grignard reagent, like in the reaction on the bottom, we get the same outcome. Notice that our epoxide starting material is asymmetric. We have a primary carbon on the left side of our epoxide and a tertiary carbon on the right side of our epoxide. Primary is less substituted than tertiary, and so that Grignard reagent is going to attack the primary carbon, the left side of our epoxide, which is going to open the ring. And in a second step, we use H3O plus to protonate the resulting alkoxide ion. And so we end up with our R group, which was a benzene ring in this case, is going to be on the left side of the starting epoxide, and the OH is going to be on the right side of our starting epoxide. So just to reiterate, when we are in acid, then the left occurs. Then we're going to get our nucleophile is going to be delivered to the more substituted side. And when we are in base, then our nucleophile is going to be delivered to the less substituted side. So this is only true when we have an asymmetric epoxide. So notice that this starting material on the top, one carbon is primary and the other carbon is secondary. So when we have a difference in the degree of substitution on our epoxide, then we have a difference in the way that it's going to react in acidic and basic conditions. So again, that reaction on the left, the acid is going to deliver the nucleophile to the more substituted side, and the base is going to deliver the nucleophile to the less substituted side.